Okay. Good morning, everyone. I guess we can get started. So today we're very glad to have Dr. Jianjun Yin, who is a professor of geosciences at the University of Arizona. Dr. Yin studies natural and anthropogenic climate change, sea level rise, the ocean's role in climate and climate change, and Earth system modeling. He is interested in broad issues of climate and climate change, in particular sea level rise, the Atlantic Meridional overturning circulation, and extreme weather and climate events. Dr. Yin holds a PhD in climate dynamics and modeling from the University of Illinois at Urbana-Champaign and conducted his postdoctoral research at NOAA GFDL. And today he will be speaking on the topic sea level rise acceleration along the US East and Gulf coasts since 2010 and its impacts on coastal flooding. So, welcome, Professor. Okay.
Okay, thank you, Patrick. Good morning, everyone. Glad to come back and present our recent work. So today I'm going to talk about sea level rise acceleration on the East and Gulf Coast and the impact on coastal flooding. So this is the outline of my talk. So I will start with some brief background and talk about the data set used in this study and the analysis methods. Then I will show the 2010-2022 sea level rise acceleration observed by tide gauge and altimetry on the East and Gulf Coast. In part four, I will discuss the mechanism of the sea level rise acceleration, especially the role of the Atlantic Meridional overturning circulation, AMOC. So in part five, I will focus on the impact of the sea level rise acceleration on coastal flooding. Finally, I will draw the conclusions. So some brief background. So sea level rise can be decomposed into a global sea level rise component and a regional deviation component. Global sea level rise is mainly caused by ocean thermal expansion and the melting of land ice, the melting of the polar ice sheet, especially. For regional deviation, there are more factors, including ocean dynamics, air-sea interactions, land subsidence, GOA changes, etc. So next, I show the observational data sets and analysis method for this study. So this table summarizes the observational data used in this study. So the sea level, water level data are from the NOAA tides and currents. So for monthly sea level data, so we use the period of 1920 to 2022, a century-long data for monthly data. For hourly data, we use the past 50 years from 1970 to 2022. So tide gauge data is a point measurement of sea level. It measures the relative sea level. For the satellite data, satellite altimetry data, we use the Copernicus data sets from 1993 to 2021. So the resolution of the altimetry data is a quarter degree. So satellite data provides the geocentric measurement of sea level. So altimetry data is for the absolute sea level rise. For ocean temperature, salinity, steric sea level, thermosteric, halosteric effect sea level data. So these data are from the NCEI, the so-called Levitas data. So the data cover 1955 to 2022, this period. So the resolution is 1 degree. So atmospheric pressure and wind data are from ERA5. So the AMOC, the volume transport by the overturning circulation, that data is from the RAPID program. So this measures the transport at the 26° north in the North Atlantic. The storm track data for tropical cyclone is from the NCEI, the NAP et al. Data sets. So this is the summary of the data used in this study. So this map shows the location and the distribution of tide gauges, tide gauge stations along the east coast and the Gulf of Mexico coast. So according to the correlation of coastal sea levels and the sea level rise rate, different sea level rise rate. So we divide the East Coast and the Gulf Coast into 5 regions. The New England region is north of New York City. So there are 12 stations in this region. The Mid-Atlantic coast from New York City to Cape Hatteras. So there are 19 stations in this region. Southeast coast from Cape Hatteras to Key West, 9 stations. And eastern and western Gulf, east and west of New Orleans. So the size of the dot indicates the different lengths of the tide gauge data. So the data can be century long at some stations. So the data is shorter at other stations. So different lengths at different locations. So we compute the annual mean sea level based on the monthly mean data. To compute the regional mean sea level curve, we first differentiate the annual mean sea level data for each station. Because different stations use different reference sea level. So to remove the impact of the different reference sea level, we calculate the difference. So HI this is the annual mean sea level in current year minus HI T minus 1. So this is the annual mean sea level in the previous year. So I is the station index. So delta HI, so this is the yearly annual sea level difference. So we calculate the regional mean of delta HI. So for the same region, so delta H bar, so this is the regional mean of yearly sea level difference. So N is the total number of stations in the same region. And with the delta H bar, so we can compute the rounding sum of the to obtain the regional mean of sea level curve for each region. So now I show you the regional mean sea level curve. So this is the sea level rise for 4 regions. The New England, panel A, B is the Mid-Atlantic, C is the Southeast, and D is the Eastern Gulf. So the red curve is the regional mean sea level curve. And the columns near the bottom is the total number of stations used for computing the regional mean. The dashed line is the long-term linear trend during 1920 to 2009. So this is the long-term trend. The number here shows the mean rise rate plus minus the 95 confidence level of the rise rate. So you can see the sea level rise. The sea level rise rate ranges from 2.4 plus minus 0.3 millimeter per year on the eastern Gulf Coast to 3.7 plus minus 0.3 millimeter per year on the mid-Atlantic coast. And another important feature is the departure of the sea level curve from the long-term trend, especially on the southeast and the Gulf Coast. So you can see the departure since 2010. And so this departure indicates the sea level rise accelerates during 2010 to 2022. So, and the decadal rise rate during 2010 to 2022 increases to more than 10 millimeter per year on the southeast coast and the Gulf Coast. So the centennial timescale rise rate and the decadal timescale rise rate are not directly comparable. So the black curve is the global mean sea level rise from the altimetry data. So the rise rate during the satellite era is about 3.2, 3.3 millimeter per year. So for the global mean sea level rise. So global mean sea level falls thought to explain the recent acceleration of sea level rise on the southeast and the Gulf Coast. Okay, so this is a update of that figure by including the last 2 years data, the 2023-24 data. So you see the on the northeast coast. So the sea level during the past 2 years were anomalously high for the New England and the mid-Atlantic region. So the sea level broke records during the past 2 years on this coast. Okay, so this plot shows the deviation of the annual sea level from the long-term trend. And the black curve is the 13-year running mean of the departure. So you can see the year-to-year interannual sea level fluctuation, as well as the decadal to multi-decadal sea level variability on this coast. The sea level rise during the past decade since 2010 is unprecedented. So you see the deviation of the sea level during the past decade. So some years in the past decade, actually, the sea level exceeded the 3 sigma, that level. The 3 sigma, so the dashed green line is the 3 sigma line. So some years actually the annual mean sea level exceeded that line. Okay, so this plot compare the tide gauge data and the altimetry data for the southeast and the Gulf Coast. So we know the tide gauge measures the relative sea level, including the land subsidence signal. But the altimetry data measure the absolute sea level, no land subsidence signal. And so you can see the altimetry data confirms the 2010-2022 sea level rise acceleration from the tide gauge observation on the southeast and the Gulf Coast. Before 2010, So you see the sea level rise was relatively slow. But after 2010, you can see the sea level rise rate increases to more than 10 millimeter per year in both tide gauge data and the altimetry data. So for altimetry data, so we just average the coastal grid points along the southeast coast and the Gulf Coast. For the tide gauge data, we just use the stations along the southeast coast and the eastern Gulf Coast. We do not include the western Gulf Coast because sea level on the western Gulf is influenced by land subsidence due to oil water extraction in this region. Okay, so now I want to discuss the mechanism of the 2010-2022 sea level rise acceleration. So the global mean sea level rise falls short to explain the regional acceleration. So the acceleration is actually the coastal manifestation of large-scale sea level change in the North Atlantic. So the left panel shows the linear trend of altimetry data for 1993 to 2021. So the global mean sea level rise is removed from this plot. So there is a large-scale pattern of dynamic sea level change in the North Atlantic. So the dynamic sea level, by definition, is the deviation of sea surface height from the GOA. So dynamic sea level falls in the eastern subpolar gyre region, in the red box region, and the dynamic sea level rises along the southeast coast and the Gulf Coast. So this is a notable contrasting pattern of dynamic sea level change. So the right panel shows the time series of the mean dynamic sea level change in the eastern subpolar gyre. So that's the blue curve, and along the southeast and the Gulf Coast, that's the red curve. So you can see the two curves diverge around 2014, 2015, and 2016. So this period, so you can see the divergence of the two curves. So the dynamic sea level fall in the eastern subpolar gyre region, it can be attributed to the steric effect. So the right panel shows the steric sea level anomaly time series from the Levitas data. So you can see the red curve here is the thermosteric sea level. So there is a thermosteric sea level fall in the eastern subpolar gyre region. And this is due to the ocean cooling in this region. At the same time, you can see the halosteric sea level rises in this region. So this is a green curve here. So this is due to the ocean freshening in this region. So the halosteric sea level rise partially compensate the thermosteric sea level fall. So if you combine the two, so you get the total steric sea level change in this region. So this is the blue curve here. So you see the steric sea level falls during this period of time. So mainly due to the ocean cooling. So by contrast, if you look at the Gulf of Mexico region, so the ocean warming caused a thermosteric sea level rise in the Gulf. This is the red curve in the left panel. And at the same time, you can see the halosteric sea level falls. So this is due to the increase of the salinity in the Gulf. And if you combine these two effects, you can get the steric sea level. There is a steric sea level rise in the Gulf region. So the coastal sea level rise acceleration reflect this mean, the basin mean sea level rise in the Gulf. So there are contrasting patterns of dynamic, steric, thermosteric, and halosteric sea levels in the North Atlantic. Okay, so this contrasting pattern is related to the slowdown of the AMOC. So the red panel shows the time series of the AMOC volume transport at 26 degrees north in the North Atlantic. So there is a slowdown event, 2009, 2010, AMOC slowdown. You can see the shading area. So you see there is a slowdown of AMOC. And the AMOC stayed at a weaker level after this event compared with the period before 2009, 2010. So you see the green lines shows the mean AMOC strength before and after the 2009, 2010 slowdown events. So in response to this 2009, 2010 slowdown, so the dynamic sea level, there is an adjustment of the dynamic sea level in the following years. In 2013, so you see there is so this is altimetry data for this 4 year. So there is a positive dynamic sea level anomaly north of the Gulf Stream. There is a negative dynamic sea level anomaly south of the Gulf Stream in 2013. In 2014, so a negative dynamic sea level anomaly region emerges at about 50 degrees north, that latitude in this region. And these negative dynamic sea level anomaly regions moved further northward into the eastern subpolar gyre region in this region during the next 2 years in 2015 and 2016. So this negative dynamic sea level anomaly is a result from the reduced northward heat transport by the AMOC due to this slowdown. So that reduced northward heat transport caused a ocean cooling in the eastern subpolar gyre region. And so the dynamic sea level falls through the steric effect. At the same time, the heat accumulation in the lower latitude raises the dynamic sea level in the subtropical gyre region, in this region, as well as in the Gulf region. So you see the evolution of the contrasting patterns of dynamic sea level during this 4 year period. So the response of the sea level to the slowdown lags the slowdown of the AMOC at a 26 degree latitude by a few years. So the arrow here is the wind. The shading is the altimetry data. Okay, to put this pattern into longer term context, so we used thermosteric sea level data from NCEI. So we remove the global mean thermospheric sea level rise from the data set, and then we perform a EOF analysis for the North Atlantic region. So for this period of time, so from 1955 to 2022 for this period. So the first EOF showing a contrasting patterns between the subpolar gyre region and the subtropical gyre region. So the PC1 showing the both the interannual to multi-decadal variability of this pattern, and at the same time there is a secular trend of the PC1. So this indicates the sea level in the lower latitude in the subtropical gyre region overall rises during this period of time, and the sea level in the subpolar gyre region falls during the entire period. And the increase of the EOF1 during 2014, 2015, and 2016 period is unprecedented. So it's unusual. It's very unusual. So the right panels shows the EOF2. So this pattern. So there is a contrasting pattern between the sea level between the slope sea area, this blue color area, and the eastern and the northern North Atlantic area. So the PC2 time series, you can see, is dominated by variability. So no clear long-term trend for EOF2. So the EOF1 explains more than 30 total variance, and EOF2 explains about 10% of the total variance. So we also looked at the role of atmospheric forcing. So the left panel shows the linear trend of sea level pressure over 2010 to 2022 period. So this pattern could not explain the sea level rise acceleration for this period. And also the right panel shows the role of the local wind. So we plot the wind together with the coastal sea level. So there is a weak correlation between the local wind and the coastal sea level. And so both the atmospheric forcing is not the local wind and the pressure are not the major driver of the acceleration. So next, I want to compare the observation with model simulations. So the panel A is the linear trend of altimetry data for 1993 to 2021. So there is a contrasting pattern in the North Atlantic. So in the panel B here is the simulation and a projection by GFDL-CM4 global climate model to generate this linear trend of dynamic sea level. So we combine the historical simulation with the SSP 4.5 projection. That's the medium emission scenario. So we combine these two to derive this dynamic sea level trend for the same period. So you can see there is a contrasting pattern in the North Atlantic, similar to the altimetry data, but the magnitude in the model simulations is somewhat larger. And on centennial time scale, so you can see the panel C is the linear trend of the dynamic sea level for 1993 to 2099. So this is centennial time scale trend of dynamic sea level in CM4. So the future increase of the greenhouse gas forcing can modify the pattern of the dynamic sea level change in the North Atlantic. So you can see the East Coast sees the largest dynamic sea level rise in response to the slowdown of the AMOC. So this is the AMOC simulation in the CM4 model. So this model simulates a vigorous overturning circulation during the 20th century. So the left panel is the overturning stream function. So this is the mean from 1950 to 2000. So this is a vigorous overturning. So in response to the greenhouse gas forcing, you see the slowdown, the weakening of the AMOC during the 21st century. So the blue curve here is the linear trend for 1993 to 2021, this period. And the green line here is the centennial trend from 1993 to 2099, this period. So overall, the AMOC weakens over the 21st century. So this is the data model comparison. Okay, so next I want to talk about the impact of the sea level rise acceleration on coastal flooding. So I will focus on the nuisance floods and also the storm surge flood. So the nuisance floods is also called the high tide floods or sunny day flood or minor flood. So the National Ocean Service set a threshold. So if the hourly water level exceed that threshold, so a nuisance flood occurs on the coast. So here I plot the number of flood days on different regions at the Battery, New York. So the Charleston, South Carolina, Cedar Key, Florida, and the Galveston, Texas. So these stations provide a high quality long-term hourly data. So you see the flood days gradually increased before 2010. So this is related to the sea level rise, the long-term sea level rise. But after 2010, you can see a rapid increase of the flood days, right? So after 2010, so for the Battery station, so the last year, 2024, here is abnormal, right? So the total flood days reached 26 days last year. Okay, so this by far broke the previous record. So on the other coastal regions, so you also see the rapid increase of the nuisance floods, right? So before 2010, you can see there are years without any floods, right? Before 2010, but after 2010, almost every year a flood occurs on these coastal regions. So this is the minor floods. So storm surge flood, so the major floods. So we looked at the hurricane-induced storm surge. So we case studied 6 hurricanes during the past several years. So including the Hurricane Harvey in 2017, Hurricane Michael, Hurricane Florence in 2018, Laura 2020, Ida 2021, and Ian 2022. So this plot shows the dynamic sea level anomaly during the hurricane season from July to October. This is a satellite altimetry data, and also storm track of tropical cyclones. And you can see the Gulf of Mexico is warm, right? And so that the dynamic sea level is high. So there is all these storms showed rapid intensification when passing over the high dynamic sea level, high ocean heat content regions in the Gulf. So you can see the rapid intensification of a hurricane in this region. And so this is the storm surge associated with this hurricane during the landfall of these hurricanes. So the red curve is the observed hourly sea level, and the blue curve is the predicted tidal cycle. So you see the shading area is the sea level rise for 1970 to 2009, this period, and also for the 2010 to since 2010. So two period of sea level rise. So the extreme sea level, extreme water level during the hurricane landfall can be decomposed into a sea level rise component and the seasonal cycle, and also high tides, right? And the storm surge. So this basically compare the relative magnitude of these terms. So the sea level rise acceleration caused about a 0.1 meter sea level rise on the southeast and the Gulf Coast. And so this magnitude is comparable to the tidal cycle because along the Gulf Coast, the tidal range is relatively small compared to the East Coast. So the largest term is the storm surge. So for these 6 storms, you can see the surge can reach 0.7 to 2.5 meters. So this is the largest term. And also different terms operate on different time scales, right? So from centennial, decadal, monthly, hourly to minute, right? So different time scales of this of different terms. So the sea level rise acceleration caused elevated storm surge during the recent years. So this is basically the time series of annual mean sea level at these stations. So you can see the different rise rate before and after 2010 at these stations. Okay, so conclusions. Both the long-term tide gauge and the more recent altimetry data reveals a acceleration of sea level rise on the US East and Gulf Coast since 2010. The acceleration is most notable on the Southeast and Gulf Coast during 2010 to 2022. So our analysis suggests that this decadal acceleration is largely a lagged response to the AMOC slowdown observed in 2009-2010. So the response is characterized with contrasting changes in dynamic sea level between the eastern subpolar gyre and the southeast and the Gulf Coast. The latest global climate model, such as the GFD-LCM4, generally captures this pattern during the satellite era. So the further increase of the greenhouse gas forcing will modify the dynamic sea level change pattern over the 21st century. And the sea level rise acceleration increased nuisance floods and caused elevated storm surges in recent years, thereby exacerbating the coastal damage. So these are the conclusion. So the references, basically the two papers on Journal of Climate. So that's it. Thank you for your attention.
Thanks so much, Jianjun. Do we have any questions? Yes, Natasha.
Hi, thank you very much for your talk. These were very interesting results and the connection with the AMOC. I have two questions, but so let me start with a simpler one. The Levitus data has better resolution higher up in the water column and more of a climatology at depth. Perhaps decadal climatology. Can you speak a little bit about what uncertainties are associated with estimating the sea level, the steric effects from Levitus?
Okay, good question. So the Levitus data, we used the upper 2,000 meters. So let's go back to that slide. Okay, so this thermosteric and halosteric sea level data from Levitus data. So, and the data is for the upper 2,000 meter depths. And the period is from 2004 to 2022. So this period of time. So this is the Argo period, right? So I think the data set incorporates the observation from the Argo program.
Mm-hmm. But would the sea level estimates from just the upper 1,000 meter not be as accurate as if you would have to include the entire depth? Or do you think most of the signal is at the top, basically?
Yeah, that's a very good question. So I think the most signal is in the upper 700 meter, 700 meter layer. So the ocean below 700 meters, so the contribution is relatively small. We did compare the steric sea level rise for the upper 700 meter and the steric sea level rise for the upper 2,000 meter. So we found that the contribution from the upper 700 meter dominates. So
yes.
Yeah, the signal,
okay.
Most of the signal from the upper ocean.
And below 2,000?
Below 2,000, in my opinion, so the contribution is relatively small because the deep ocean is relatively uniform, right? So, and the change is smaller compared with the upper ocean change.
Thank you.
Mm-hmm.
Thank you.
Yeah.
Well, if there is no other question, I have another one too about the GFDL model result. It has a very interesting decline in the AMOC, which is in the 21st century, which seems to be stronger than the observations somewhat. That doesn't matter, but it has a stabilization after 2050. Yes, there. And I wonder if you've seen, what signal do you see in the sea level?
So overall, the AMOC weakens. So you said that there is this AMOC levels off after 2050. So remember, this is a medium projection. So we used SSP 245 for this projection, and in higher emission scenarios, so you see continuous weakening.
Yes. And how does the sea level respond after 2050?
That's a good question. I did not specifically look at the pattern after 2050. I think without further weakening, So the sea level response should be relatively small. So the response is mainly for the first half of the 21st century in this model. Yeah.
Thank you.
Okay, Jimmy.
Hi. So can you all hear me?
Yeah.
Hi. Hi, thanks. Can you go to the previous slide? I think I have a question related to it. Yeah, thanks. So in the explanation for the current situation, or the recent past, I think I followed what you were saying. I missed if you had found a way to convince yourself that there isn't some signal from changes in the wind forcing affecting the gyre that's at play. And then related to that, if we look at panel C, what's the link in the mechanism that you started out for the current explanation that explains the shift in where the maximum change in the trend is occurring? So it feels to me like a subtropical gyre versus subpolar gyre signal when you go from the early to the late, or the longest term, panel C.
Okay, so yeah, the different response time between the northeast coast and the southeast coast. So you see, for the satellite arrow, so we also see the signals, dynamic sea level rise signal, just offshore in the slope C region, because the upstream of Cape Hatteras, so the Gulf Stream flows very close to the coastline, right? So if there is some change associated in the current system, so the coastal sea level may immediately respond to that change in the current system. But the Gulf Stream is further offshore, downstream of Cape Hatteras, right? So I think it takes time for the signal to propagate onto the shelf. So if you look at the centennial timescale projection, so you can see the signal well propagated onto the shelf, right, from the slope C region onto the shelf. So I think it's related to the distance of the current system from the coastline.
Interesting. And then, do you have an interpretation for why the signal in the Gulf weakens on the really long time scale?
I'm sorry.
Was the signal in the Gulf is the strongest signal in the recent past?
Yeah.
And I was wondering if you had thoughts on why that eventually becomes pretty small as compared to what's happening up on the shelf region.
Yeah, that's a very good question. So we are not very sure why the response time in the Gulf is different from the response time for the other region. I think this is a possible next research topic. So why the response time is different at different regions? Yeah.
Okay, thanks a lot.
Yeah, thank you.
Any other questions? So I was actually wondering about the drivers of the AMOC slowdown and the emerging pattern that you see. Is that related to cryospheric changes, or are there also other processes?
So you mean why the AMOC weakens during the first? So that's a robust feature in the model projections. So the weakening can attribute to the the warming, ocean warming, and also ocean freshening at the high latitude North Atlantic. So with the greenhouse gas forcing, the upper ocean gets warmer, right? And also the melting of the Greenland ice sheet also can provide meltwater flux into the high latitude North Atlantic. So both the warming and the freshening can reduce the upper ocean density, right? So the ocean can become more stratified in the high latitude North Atlantic. So that can inhibit the ocean deep convection and also the deep water formation. So eventually that can cause the weakening of the overturning circulation.
Okay, great.
Yeah.
Any other questions?
Yes, in response to also a question following up on this, does GFDL have prognostic ice sheets? I don't think so.
Oh yeah, that's a very good point. So the model does not have a interactive ice sheet. Yeah, so
but it's probably but it's parameterizing some additional freshwater inputs.
Yeah, but there is no interactive ice sheet model. So that's a good point because without the meltwater from the Greenland ice sheet, so the change of the AMOC could be underestimated in the model. Yeah.
Great. Any more questions? Well, I guess we can stop there. There's no more questions. So thanks again, Professor Yin.
Thank you, everyone.